Hello everyone. Today I'll talk about our RL work on probabilistic point cloud modeling via self-organizing Gaussian mixture models. This is a collaboration with Nathan Michael and Vanita Veeb at Carnegie Mellon University. The key motivation behind this work is to create compact high-resolution point cloud modeling method for mobile robot exploration. Specifically, we want to create a point cloud model that enables compactness for memory-efficient operations, occupancy mapping for safe navigation, and reconstruction to create high-resolution maps. Towards these three goals, various point cloud modeling approaches have been proposed. The most popular ones are the Octomap, Entity Map, and Voxbox methods. Typically, these methods optimize for only a subset of these goals. To bridge this gap, recently Gaussian mixture models have been proposed as point cloud models that can achieve all three objectives. However, a key problem with the GMMs approach is that we need to guess the complexity parameters, such as the number of mixture components in the GMM, for every new scene that the mobile robot is supposed to explore. In this work, we provide a solution to this problem using an information-theoretic principle called the principle of relevant information. At a high level, PRI works as follows. Let's say we are given a dataset which contains IID samples from an unknown density PY of a 2D continuous random variable y. Our objective is to compress dataset y into y sub r. We write this problem as an information-theoretic optimization. The objective function is given by a weighted sum of the Renai entropy of the compressed dataset and the Cauchy-Schwarz divergence between the compressed and the original dataset. The entropy objective reduces the amount of redundancy in the dataset, and the divergence objective reduces the amount of error. For different values of the weighting parameter, we get different results. For beta equals 0, we get a featureless solution where the dataset just collapses to a single point. For beta equals 1, we get the dominant modes of the dataset. And for beta values greater than 1, we get the principal curves of the dataset. We use the value beta equals 1 and leverage the number of modes in the image data as the number of mixture components for the GMM. Let's see how well SOGMM can adapt to the model complexity of the environment. On the left, we see two images. Image A has a lower complexity, and image B has a higher complexity. For these two images, we plot the number of estimated components M against the range of bandwidth parameter sigma for the PRI principle. We make two observations. First is that for every bandwidth parameter, the estimated model complexity for image B are higher than image A. And two, overall, lower bandwidth parameter leads to a higher model complexity. Thus, the SOGMM method is able to adapt the model complexity to the amount of complexity that's there in the image. The qualitative and quantitative results from the experiments in the paper are shown here. For the Octomap method, we observe somewhat pixelated output. This is expected as that it represents the environment discretely. The output of Entity Map method is smoother because of its use of 3D Gaussians, but it fails in terms of the compactness objective. Finally, the SOGMM method provides a higher quality 3D reconstruction while enabling higher PSNR score, indicating better intensity reconstruction at a lower memory cost. We are able to estimate the number of mixture components required to model a scene, given a pair of depth and intensity images, and in a way that balances the compactness and the fidelity of the model. In conclusion, we have proposed a method to probabilistically model a multimodal point cloud using self-organizing Gaussian mixture models. I'll be happy to talk more and answer questions about this work now or during the poster session.